The lesson today is on chemical equilibrium. Now, we're all familiar in everyday life with reactions that go in one direction only, such as combustion reactions. For example, if we burn oil or coal or gas, a chemical reaction is taking place with oxygen from the air, and we get carbon dioxide and water produced, and of course some heat is produced as well. This is an exothermic reaction. But we can't take carbon dioxide and water and heat them up and go back again to oil or coal or gas. No, this reaction goes in one direction only. But there are a number of reactions which are actually reversible. They go in two directions. For example, I could have a substance A reacting with a substance B to form a substance C and another substance D. And once C and D are formed, they could react with each other to form A and B again. Now, if we have these substances in a closed system where nothing can escape, what happens is this. Initially, when there's only A and B and they start to react, the forward reaction is fast. When C and D are formed, initially there's a very small amount, and therefore the reverse reaction is slow. But as C and D build up in quantity, this reaction speeds up. And because A and B are reacting and therefore diminishing in quantity, the forward reaction slows. Now, if we leave these substances in a closed system, eventually the rates of reaction in each direction will become equal. Now, once that happens, we have reached what is known as a state of dynamic equilibrium. Equilibrium, what that means is that the rates of reaction in each direction are equal, they are the same. It doesn't mean the quantities A, B, C and D are the same. It may happen, but it's highly unlikely. No, it refers to the rates. Dynamic, that simply means that there is continuous change going on all the time in both directions. A and B, C and D are continuously reacting. But because it's happening at the same rate, it means that at equilibrium, the amount of A and B and C and D present are constant. Not equal, but constant. Now, what we want to look at today are the factors that will affect what we call the position of equilibrium. Position of equilibrium? Well, essentially that refers to the relative amounts of A and B and C and D that are present at equilibrium under a given set of conditions. Now, to do that, we want to look at a reaction which is well known. It's called the Haber process, named after the man who first devised it. It is the process for making ammonia on an industrial scale. Now, in this reaction, we're taking nitrogen, which is a gas, reacting with hydrogen, which is also a gas. It's a reversible reaction, and ammonia is formed, which is also a gas. And of course, heat is also generated as the ammonia forms. Delta H is negative. This reaction is exothermic. We just balance that by putting a 2 there, a 3 there, and a 2 there. Now, we want to consider, if we change certain factors, what will happen to the relative amount of nitrogen, hydrogen and ammonia at equilibrium. Now, the factors that we wish to look at are temperature and pressure. What will happen to the position of equilibrium if we tamper with the temperature and or the pressure? Now, we're going to look at changes in temperature first. We're going to keep the pressure constant and change the temperature. Now, if I have these three substances in a container from which they can't escape, I've got nitrogen, got hydrogen, and I've got ammonia. millions of each of these types of molecules all coexisting. And I have this container in a room, say at 25 degrees centigrade. Now if I lift the container and put it in a fridge, say at 4 degrees centigrade, in other words, I'm dropping the temperature, the system has been cooled. What happens to the position of equilibrium? Now, to understand that, we have to consider what is known as Le Chatelier's principle, called after the man who first devised the principle. And Le Chatelier's principle says this: if a system is in a state of dynamic equilibrium and we change any of the conditions to which it is exposed, then the system will respond by trying to minimize or undermine or nullify the effect of that change upon it. So, how does this work out in practice? You put the container into the fridge. The system has been cooled down, it's cooler there. According to Le Chatelier, the system will react to undermine the effect of that cooling. The only way it can do that, of course, is to produce heat. The only way it can produce heat is to produce more ammonia, because that is an exothermic reaction which gives out heat to the surroundings. So, the moment I put that container into the fridge, the equality of the rates is disturbed. And more ammonia starts to be produced. That reaction going in the forward direction speeds up. It gets faster to produce more ammonia. Of course, when you get more ammonia produced, this begins to speed up. This gets faster too, it speeds up. Nitrogen and hydrogen are beginning to diminish. It slows. But eventually, if we leave this system in the fridge, a new state of dynamic equilibrium will be produced, where the rates of reaction in both directions will become equal again. But when they do so, the position of equilibrium will have shifted to the right. There will be more ammonia present in the fridge than there was out in the room at 25 degrees centigrade. Now, what would happen if we raise the temperature? Now again, we've got our container in the room at 25 degrees centigrade. If I put it in the oven, say at 100 degrees centigrade, again, the equality of the rates will be disturbed. According to Le Chatelier, the system will respond to try and undermine the warming effect of the oven. Now, the only way it can do that is to absorb some of the heat. Now, the reaction going to the left is endothermic. Delta H is positive. This reaction proceeds by absorbing heat from the surroundings, and that is what happens. The reaction in that direction speeds up, and eventually, if we leave the container in the oven, the two rates will become equal again, and a new state of dynamic equilibrium will be produced. But the position of equilibrium will have shifted to the left. There will be less ammonia now than there was out in the room at 25 degrees centigrade, and there will be more nitrogen and hydrogen. So we can see that Le Chatelier's principle explains to us very nicely what happens when we change the temperature constant pressure. Now we want to look and see what happens if we keep the temperature constant and we vary the pressure. Now to do that, I want to refer you to the ideal gas equation, where PV equals nRT. Where P is the pressure, V is the volume of the container, N is the number of molecules of gas in the container, R is the gas constant, and T is the temperature on the Kelvin scale. I can rearrange this and say P equals N RT over V. Now, R is the gas constant, it's constant. We're keeping the temperature T constant. V is the volume of the container, it's not changing, it's constant. Therefore we can say that P, the pressure, is directly proportional to M, the number of molecules in the container. And that's what we want to keep in mind as we apply Le Chatelier's principle to this situation. Now, constant temperature, nothing can escape from the container, and we're going to increase the pressure. If we increase the pressure according to Le Chatelier, that means the system will respond by trying to undermine that, by trying to reduce its pressure. Now remember we said that P is directly proportional to M. The more molecules present, the greater the pressure. The fewer molecules present, the lower the pressure. Now I want you to look at this equation. On this left-hand side here, we have got 1 mole of nitrogen, 3 moles of hydrogen. Together, that's 4 moles. On the right-hand side, we've got 2 moles of ammonia. So the more this system exists in the form of ammonia, the fewer will be the overall number of molecules inside the container. The more this system exists in the form of nitrogen and hydrogen, the greater will be the number of molecules within the container. So if we're increasing the pressure on the system will try to lower its pressure. In other words, it will try to exist as fewer molecules. Now, to do that, it produces more ammonia. And the reaction towards the right speeds up. As before, if we leave the system at that pressure, eventually the rates will become equal again. A new state of dynamic equilibrium will have been produced, but the position of equilibrium will have shifted to the right. In other words, there will be more ammonia present at the higher pressure than there was before. Now conversely, if we lower the pressure, the system will respond by trying to increase the pressure. The only way it can do that is to exist as more molecules. That means the reaction that way will speed up. And as before, if we leave the system under that lower pressure, the two rates will eventually become equal again. A new state of dynamic equilibrium will have been produced, but the position of equilibrium will have shifted to the left. There will be less ammonia and more nitrogen and hydrogen than there was at the higher pressure. Now, ideally then, if we want to maximize our yield of ammonia, we would want a very low temperature and a very high pressure. That would give us more ammonia. But we have to live in the real world. This has to be an economical and a practical process in the industrial preparation of ammonia. So a compromise is needed. If we lower the temperature too much, it will slow the rate of reaction down. In fact, lowering the temperature will slow all reactions down. Now, it will give us a good yield of ammonia, but it will take a long time to get that yield. So to get a reasonable amount of ammonia in a reasonable amount of time, we have a moderate temperature of about 400 degrees centigrade. Similarly with the pressure, if the pressure is very high, it becomes expensive. There's an economical factor. Also, high pressures are potentially dangerous. There's health and safety consideration as well. So again, a compromise of a moderate pressure. So in the practical application of the Haber process for reducing ammonia, we use a moderate temperature and a moderate pressure, which gives us a reasonable amount of ammonia in a reasonable amount of time safely. One other thing I would mention is a catalyst. If an iron catalyst is added to the system, the catalyst speeds a reaction up, but it does so in both directions. Therefore, it does not affect the position of equilibrium. It will not increase the amount of ammonia that we get, but it will result in us getting a certain amount of ammonia more quickly with the catalyst present.